conditional statements for geometry. So the goal for today's lesson is going to be able to write definitions as conditional statements. So we'll get into what are conditional statements in a minute. Now, the reason that we are covering conditional statements before we jump to deductive reasoning, or our previous lesson, I should say, we looked at inductive reasoning. Well, the idea is that we need conditional statements first before we can apply deductive reasoning. So today's lesson is basically around this idea of conditional statements, which are logical statements with two parts, a hypothesis and a conclusion. So our conditional statements are mathematically logical statements that have two parts, a hypothesis and a conclusion. Now, in mathematics, remember that a single statement is either true or false. In this case, because we are putting together two different statements, then we have to connect them with a conjunction. And the way we do that mathematically is we write them in an if-then form. The if part always will contain our hypothesis. The then part, so what follows if is the hypothesis, what follows the word then contains the conclusion. So an example here, if it is raining, then there are clouds in the sky. It is raining would be the hypothesis. Then there are clouds in the sky would be the conclusion. Now, our goal says to write definitions as conditional statements. In mathematics, a lot of the time, we try to write definitions in the form of conditional statements to clarify what they mean and to make sure that they are in a consistent format. Doesn't always happen, but that is one of the main goals. So let's look at example one though. First, just to write conditionals in if-then form. So in A, we are given this statement, you have a fever if your body temperature is 103 degrees. So I can rewrite that as if your body temperature is 103 degrees, then you have a fever. So we're just rearranging this into an if-then statement. They already gave us the word if, so I knew my hypothesis, if your body temperature is 103 degrees, our conclusion that you have a fever. In B, a deer is albino if it has white fur and pink eyes. So we could rewrite that to say, if a deer has white fur and pink eyes, then it is albino. And then in C, it says, I'll buy that CD for you if you want it. So we're rearranging again. If you want that CD, then I'll buy it for you. So conditional statements, simply written as if-then statements. Then we get into 4 different terms related to conditional statements. Negation is the opposite of the original statement. So we're looking for something like the word not. So the opposite would be including that idea of not. If you do not want that CD, then I will not buy it for you. Converse. The converse of a statement is where the hypothesis and the conclusion have been exchanged. So if we look at C again, our original is if you want that CD, then I'll buy it for you. The converse, we need to flip the conclusion and hypothesis. So this would read for our converse, if I buy that CD for you, then you will want it. The inverse is where we are negating both the hypothesis and the conclusion. So we're reversing them or adding the word not. So in C, again, using this as our example, if this is our original conditional statement, the inverse would say, if you do not want that CD, then I will not buy it for you. So we're negating both the hypothesis and conclusion, making them the opposite. And then the last phrasing is a contrapositive. And a contrapositive is written in converse form, and then both the hypothesis and conclusion are negated. So if I look at C again, this is my original statement. My contrapositive would be flipping the hypothesis and conclusion first, and then negating both. So that would be, if I do not buy that CD for you, then you will not want that CD. So example 2, they're asking us to write the converse, inverse, and contrapositive of the if-then statement. So our original statement was given to us, the original conditional on top. If water is frozen, then its temperature is below 0 degrees. So obviously they're talking Celsius. So our original, if water is frozen, then the temperature is 0 degrees. The converse tells us we want to, look here, reverse the hypothesis and conclusion. So we're just going to flip the order, and it would say, if the temperature is below 0 degrees, then the water is frozen. Our inverse is taking the original statement and negating both the hypothesis and the conclusion. So the inverse would say, if the water is not frozen, then the temperature is not below 0 degrees. And our last type, the contrapositive. So we are looking at the converse, and we are negating it. So if we take the converse, if the temp is below 0 degrees, then the water is frozen. We're just rewriting the converse, but the opposite in each part. So it would read as, if the temperature is not below 0 degrees, then the water is not frozen. So in B, if x plus 3 equals 5, then x equals 2. So our hypothesis, x plus 3 equals 5, the conclusion, x equals 2. So the converse, we flip our hypothesis and conclusion. So if x equals 2, then x plus 3 equals 5. The inverse is the original statement, but negated. So the way we negate the equal sign is turn it into a not equal. So if x plus 3 is not equal 5, then x is not equal 2. And the contrapositive is taking our converse and negating it. So if x is not equal 2, then x plus 3 is not equal 5. Now, example 3, they give us just a statement. They first want us to write it as a conditional, then the converse, the inverse, and the contrapositive. And then we're going to say if each of these individual statements are true or false. Now there is a shortcut to this. The original statement, so our original conditional statement, so if we look at A, if it rains, then it pours. That's our original conditional statement. If our original is false, the contrapositive is automatically also false. If the original is true, then the contrapositive is automatically true. Same thing with the converse and inverse. If the converse is true, the inverse will always be true. If the converse is false, the inverse will always be false. Or you can read each statement and just say if they make sense or not. So in A, we're taking when it rains, it pours, first writing it as an if-then conditional. If it rains, then it pours. That's false, because we have plenty of types of rain where it's not pouring. A mist, a sprinkle, a light shower. The converse, if it pours, then it rains. That's true, because in order for it to be pouring out, it first has to be raining. The inverse, if it doesn't rain, then it doesn't pour. That's also true. If there's no rain, there's no possible way it's pouring. And the contrapositive, if it doesn't pour, then it doesn't rain. That's false. So in B, they gave us the statement, any four collinear points are coplanar. So to turn that into an if-then statement, we would say, if 4 points are collinear, so any 4 collinear points becomes, if 4 points are collinear, then they are coplanar. Well, in order for 4 points to be on the same line, they all have to be in the same plane, so that is true. The converse, we're flipping our hypothesis and conclusion, so we'd say, if 4 points are coplanar, then they are collinear. That is false. We can have 4 points in a plane, not on the same line. The inverse, if 4 points are non-collinear, then they are non-coplanar. We could also say if 4 points are not collinear, then they are not coplanar. That is false. In our contrapositive, if 4 points are non-coplanar, then they are non-collinear. And because our original is true, the contrapositive is always the same or true. Then we're moving into our last few pieces here. Perpendicular lines. Perpendicular lines are 2 lines that intersect to form a right angle. So perpendicular lines intersect to form a right or 90-degree angle. So example 4 says use the previous statements. So our statement about perpendiculars, the diagram over here, and the definitions or properties that you have learned to explain why the statement is true. So we're explaining this definition based on all the info here. So line AC is perpendicular to line BD. Line AC intersects BD at 90 degrees. So it's true, the right angle symbol shows us they intersect at 90 degrees. Angle E, or angle AEB, and angle BEC are adjacent angles. AEB is the angle right here, BEC is the angle right here. They share a vertex and common side, so they are adjacent angles. That is true. In C, angle AEB, so this angle here in the upper left again, and BEC, the one in the upper right, are a linear pair. That's also true because of the angle addition postulate, meaning if 2 angles add to be 180 and they're adjacent, then they are a linear pair. And in D, the measure of angle AEB, right here, plus BEC, is 180 degrees. That's also true because if they are a linear pair, lines are 180 degrees, so based on that definition of a linear pair, these lines add to 180. And then our final idea for today is the idea of biconditional statements. I apologize, my example C shifted to another page when I printed it. But biconditional statements are a statement that contains a phrase if and only if. So biconditionals have to have if and only if. This is used when both the original statement and the converse are true. So if the original and converse are true, we can write a biconditional. So example 5 asks us to rewrite the definition in an if-then statement, then write the converse of the if-then statement, and then we're writing it as a biconditional. So example A says the midpoint of a segment is a point that divides the segment into two congruent segments. So first rewriting that as an if-then statement. We could rewrite that as if the point is a midpoint of the segment, then it divides the segment into two congruent segments. So in blue there is our original if-then. Then the next part of the directions asks for the converse. So our converse would be flipping the conclusion and hypothesis. So our converse in A, if a point divides a segment into two congruent segments, then it is the midpoint. Both of those are true, so we can write a biconditional. Our biconditional, here kind of in pink, says a point is the midpoint of the segment if and only if it divides the segment into two congruent segments. So now we're taking that idea and rewriting it with the phrasing if and only if from the original statement. In B, now I only wrote the biconditional for this one. I decided not to write the original and converse because we practiced that quite a bit already. So in B, I just wrote the biconditional. So our original says two angles are complementary angles if the sum of their measure is 90 degrees. So rewriting that as a biconditional, I would say two angles are complementary angles if and only if the sum of their measure is 90 degrees. And our last example, example C, again, just rewriting it as a biconditional. So in example C, it says, in an equilateral polygon, all sides are congruent. So we could rewrite that and say a polygon is equilateral if and only if all sides are congruent. So on top of biconditionals, the if and only if, the other key pieces for today's lesson come back to this original idea of conditional statements being written in if-then form, using the hypothesis and conclusion, and then the idea of negating, adding not or the opposite, converse, when we flip the hypothesis and conclusion, the inverse, when we negate the hypothesis and conclusion, and the contrapositive, when we take the converse and negate both parts.